Hello. In this video, I want to talk about the difference quotient. The difference quotient is an idea that's covered in many algebra classes, and it's covered as a precursor to a very important topic in calculus. So in this video, I want to show you what the difference quotient is, kind of the formula for it, and it's written in a couple of different ways, so I'll show you those ways. We'll talk about what this actually means graphically. We'll look at some examples where we can do some calculations for calculating difference quotients. And then after that, we will end with just a little brief kind of a look forward as to where this ends up being useful in calculus. So let's start off by looking at the difference quotient. When we have the difference quotient, the assumption is that we're dealing with some function f of x. And there's a couple of ways to write this, depending on your instructor. You might see one or both of them. So one way to write it is f of a plus h minus f of a all over h. And another way that you might see it written is f of x plus h minus f of x all over h. Now, if you look at these, you'll recognize that they're basically the same formula, but one of them has an a in it, and the other one has an x in it. They're really both the same thing. It's just different instructors and different books introduce things kind of at different speeds and in different ways. So you might see it one way or the other. Basically, they mean the same thing. I want to talk about what this means graphically before we go into any numerical examples. So we would only really look at the difference quotient if we had a function, some function y equals f of x. And so I'm just going to take a graph of a function. Looks kind of like a parabola. It doesn't have to be a parabola. It's just an easy shape to go with. And so what we're doing is we're looking at the function at some value, x or a. It doesn't really matter which you pick. Let's pick a because that's often how it's introduced in the beginning. And so we might have this function value at a. So this height would be f of a, and then the x value there is a. And then we're also going to be looking at the function at another point, and that's going to be a plus h. And so basically we're going to have another point, and the x coordinate of that point is a plus h. That might seem a little bit weird at first, but if we have two points on the x-axis, two values on the x-axis, a and a plus h, what this means is that the distance between them is actually h. So instead of referring to these points as a and b, for example, what this difference quotient does is that the variables inside the a and the h refer to the first, our starting point, and then the distance along the x-axis to the second point. So this second point is our a plus h, and if we were to make a little dotted line that goes across to the y-axis, then that would be the y value or the function value f of a plus h. And so we have the difference quotient, and if we look at the numerator, this is the difference of the function values. This is the difference of the y values. So the numerator is going to be this distance here between the 2 points vertically, and then the denominator is h, which is the distance between them horizontally. If we were to actually draw in a little triangle here, this height would be the numerator, f of a plus h minus f of a. It's the difference of the y coordinates. And then the bottom would be h. the denominator is that change in the horizontal distance, you might already be recognizing that if we look at that quotient, that gives us the slope of the line that goes through those points. It's basically a more complicated way of writing rise over run. So the difference quotient gives us the slope, the slope of what's called the secant line. A secant line is a line that goes between 2 points on a graph. So this difference quotient is giving us the slope of the secant line, the line that goes between the 2 points on the graph. Now, sometimes you will see all of this introduced just like I have, where the x values are a and a plus h, and oftentimes we will start off by picking values of a and h and doing these sorts of calculations, but eventually we want to move, instead of looking at particular values of a, we want this difference quotient to be based just off of x. If we have a function f of x, then this actually becomes another function of x for a given value of h. Now, why do we care about the slope of this line that goes between a couple of points? Well, this ends up being really useful information if our function represents some sort of a real world thing. If this function represents the height of a rocket ship, then that's launching into space, for example. Not that that would make sense because rockets don't go down before they go up. But if, for example, we had a function that represented that, then the y value is the height and the x value could be time. We could be looking at the height over time. And the slope of this line would give us the average speed of the rocket going vertically between those two times. So if we have a function that gives us position, then the difference quotient ends up being a calculation that gives us the average time, or the average speed, excuse me. You might have seen average rates of change in your class as well. It's a topic that's very much related to this. And so that would be really useful for knowing the average speed over time. And then if it was a different sort of a function, there might be other implications for looking at the average rate of change or for looking at the difference quotient. But what I want to do is I want to do a couple of examples looking at the difference quotient, and then I want to talk about what you'll see in a calculus class, how calculus will take what we're doing here and push it one step further. So a very common example for average rates of change, and I'm going to use the second formula. We're going to jump straight into x's instead of a's. A very common one to see is f of x equals x squared. So let's evaluate the difference quotient for this function. So we have f of x plus h minus f of x all over h. Now, if we want to know what f of x plus h is, this function f takes the input and squares it. So f is going to take in x plus h, and it's going to give us x plus h quantity squared. That's what the function does. It squares the input. And then minus f of x is just x squared all over h. Now, there is definitely some algebra to do here. We need to square x plus h. And if you do that, you can FOIL it out, or you might remember the formula for the square of a sum. It's going to be x squared plus 2hx plus h squared. And then we also have minus x squared that we need to keep. And that's going to be all over h. Now, if we look at the numerator, we can see that the x's are going to end up canceling, because there's a positive x squared and a negative x squared. And so that's just going to leave us with 2hx plus h squared over h. And then we can divide both of those terms by h, and that gives us 2x plus h. So the difference quotient for the function f of x equals x squared is going to be 2x plus h. All right, let's do another example. I want to do a different one, and then we're going to kind of talk about what this means and compare them, and talk a little bit about calculus. So let's look at a linear function next. Let's look at a function like 3x plus 2. So again, we're going to use the formula f of x plus h minus f of x all over h. So f of x plus h is going to be 3 times x plus h plus 2. So we've got 3 times x plus h plus 2. And then minus our f of x. And the f of x is 3x plus 2. So we're going to subtract 3x plus 2. And we need parentheses there because we're subtracting that whole quantity. And this is going to be all over h. Now we can distribute that 3. That's going to give us 3x plus 3h. And then we also have the plus 2. And then when we distribute the subtraction, we're going to have minus 3x and minus 2 all over h. And if we look to see if anything cancels, we've got a positive 3x and a negative 3x. We've got a positive 2 and a negative 2. And when those cancel, we're left with 3h over h. And when we divide 3h by h, that gives us just 3. So we got 2 very different answers for the difference quotient for these 2 different functions. And I want to talk about why we got different answers, and I want to talk about what they mean, and I want to kind of look forward into what we're going to see in a calculus class. So remember that the difference quotient gives us the slope of the line that goes between 2 points on the graph. And those points have x coordinates x and x plus h, or a and a plus h, depending on which variable you're using. Now, this is a linear function. We know that its graph is just going to be a line. And so if we're thinking about the difference quotient, and that gives us the slope of the line between 2 points on that graph, well, no matter which points we pick on a line, the line that goes through those points is going to be that line, and the slope of that line is 3, and so the difference quotient is going to be 3 no matter where we look, right? Linear functions are the sort of function where the slope, the steepness, is the same no matter where we look. And so that's why the difference quotient doesn't have any variables in it, like x or h. We're going to have the same steepness no matter which points we pick on that line. If we look at the other function, f of x equals x squared, we know that that's going to be a parabola. And depending on the points that we pick, if we pick, a pair of points like these two, we're going to have a positive slope. But if we pick a pair of points like these two, we're going to have a negative slope. And the slope very much depends on both of the points that we choose. And because it depends on both of the points that we choose, both of the x values, the answer, which is going to be that slope of the secant line, is going to depend on our choice of x and our choice of h. So that's why we get something that's more complicated here than we do with the linear function. Now, when you get to calculus, you're going to be wanting to find the slope, not of a secant line, a line that goes through a graph at 2 points, but you're going to want to look and see how steep a graph is just in one place. And the way that we actually do that, if we want to know how steep a graph is in one place, it's really the steepness of the tangent line, the line that touches it in one point. That's not the best tangent line that's anyone's ever drawn, but I'm on an iPad. It's not perfect. But that ends up being a lot more complicated because with a secant line, we can pick 2 points, and it's very easy to calculate the slope of a line that goes between 2 points. It's rise over run, in this case written as the difference quotient. However, when we only have 1 point, we can't do rise over run anymore because we don't have the 2 points for inputs. And so this becomes a more complicated problem, and it's something that you're going to spend a fair bit of time in calculus working on. Now, the way that we do this in calculus, and I'm just giving like a little 1-minute intro, is we take our first point and we keep it where it is. Maybe that's the point where we want to find the steepness. And we take the second point and we look at what happens when that second point gets closer and closer to the first point. If we were to take the second point and we were to move it, for example, to here, that gives us another secant line. And then if we move it even closer, that gives us another secant line. And the closer and closer we move it, the closer and closer the slope is to the slope that we actually want. There's something kind of complicated called a limit involved that we're not going to talk about now. But basically what we want to do is we want to take this distance h and we want to make it smaller and smaller and smaller so the points are getting closer and closer together, and they give us a better and better approximation of what the tangent line's slope would be. And so what you're going to be doing is you're going to be looking at the difference quotient when you're in calculus. So here we've got 2x plus h, and you're going to look at what happens to it as that distance h gets smaller and smaller and gets closer and closer to 0. And when this h gets smaller and smaller, you know, it might start off at 5, and then it's 1, and then it's 0.1, and then it's 0.01, and then it's 0.0001. This becomes negligible compared to the 2x. And it turns out that if we want to know the slope of the tangent line to the parabola y equals f of x, for any x value, the slope is going to be 2 times that x value. So this is something that is developed much more rigorously in calculus. You spend a lot of time on it. It's not just a quick couple of minute segue at the end of something else, but this is where we're eventually headed in a calculus class. And so it's important to get good practice with the difference quotient so that when you get to a calculus class, it's easier to do those sorts of calculations.